We're going to finish up this section on pre-calculus talking about different types of functions that we really haven't gone that in depth with. I know we have talked about absolute value functions before this point and rational functions before this point, but I want to revisit them a little bit deeper. Piecewise defined functions, I find that students don't like them, but hopefully we can get to a point where you understand the different pieces much better and get comfortable with piecewise defined functions, because we will see them in our calculus work, and they really honestly couldn't be easier to work with. And then finally, it's important that we deal with data that's given to us in a table form in such a way that we don't feel like we need to graph that data in order to understand it. We need to be just as good getting information and interpreting information from information given to us in tables as well as we are already with information given to us graphically. I want to take a moment here to talk about the density of the real number line. It's important, especially when the idea of infinity continues to come up for us over and over and over in our calculus work. I want you to have a clear idea of just how big infinity is, and a clear idea that when we tell you we have a real number line that contains infinitely many numbers along it from negative to positive infinity, I want you to have a much clearer idea of exactly what that means. So on the real number line, we'll just take a horizontal number line. We recognize that if we continue to go in this direction, we will wind up at positive infinity. If we continue to go in this direction, we're headed toward negative infinity. The center of the real number line, we could call that point where the real number that is allocated to that tick mark on the real number line is 0. We might call that the center. Everything to the right of it are positive input values or positive numbers. Everything to the left would be negative numbers. I want you also to understand that in between any two arbitrary tick marks or points on a real number line, because of the density of this real number line, there is another real number. Pick any two numbers. We'll pick 0, and we'll pick 0.00000 ... that contains infinitely many zeros, 001. Those two numbers are in very close proximity to each other along the real number line. But understand, in between those two numbers is another real number. And in between 0 and this real number, and then over here this number, in between those two is another real number. And in between those two is another real number. And in between those two is another real number. As a matter of fact, find any 2 points on the real number line. I don't care how close they are to one another. There are infinitely many points in between any 2 numbers on the real number line. That's dense. Dense, 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 dense. That's extremely dense. I want to also give you the idea that here, when I said we go to the right to positive infinity, we are never at positive or negative infinity. The definition of infinity, positive or negative, is large without bound. It's so large, we can't even tell how large it is. It's large without bound. We will never be at infinity. The best we can ever hope to do, let's just write that down, the best we can hope to accomplish is to get near infinity. Infinity is an idea. Infinity is not a value. This symbol has no specific value. This symbol is an idea of a large quantity. How large? However large you think infinity is, we can always find another number to the right of it, and that infinity will be bigger than the one you thought of. So when we deal with infinity, we're dealing with an idea. That's why when infinity comes into play in our work, I never want to see you pick up that infinity symbol and do a mathematical operation on that infinity symbol. This is a no, no, no. Never pick up the infinity symbol and perform a mathematical operation on it. I don't care if you substitute it with the word huge. I'm okay with that. I can go there with you. I understand huge input values into a function that leads to corresponding output values. But because infinity is not a real number value, it's just an idea, and it has no specific value attached to it, don't ever pick the symbol up and mess with it as if it were a number. It is an idea. And because the real number line contains all real numbers from negative infinity, but not including negative infinity, all the way up to positive infinity, but not including positive infinity, the real number line is so dense, we really can't get a really good idea of just how dense that is. Think of every person that has ever lived on the face of the planet. Now, there's several billion of us here right now. Think of everyone that has ever lived on the face of this planet throughout history. That's billions of people. That doesn't even touch what's going on between any two arbitrary points on this real number line. There are more points on this real number line between these 2 points that I just drew than there are cells of every living creature that's on the face of the planet now, that has ever been on the face of the planet, that is floating out in space, that is on any other planet in our solar system or in all solar systems. The idea of the denseness of the real number line truly is a mind-blowing idea. I want you to get a clear idea of just how dense the real number line is. I also want to do a quick review. I know we've talked about this a little bit as we were talking about domain and range and things like that. But here are all of the set notations given an interval of values of something. Here we're talking about horizontal values, so we might call these domain values. We have an open interval, which is evidenced by neither endpoint being included in the set. This is the set of all real numbers from -1 to +1 along the real number line, not including the endpoints. -1 is not included in this set, and +1 is not included in this set. This is an open interval. You probably could put that together in your head because we have open endpoints maybe. A closed interval, instead of parentheses, we're going to use brackets. This is the interval of all real numbers from -1 to +1, including the left endpoint of -1 and the right endpoint of +1. Both of them are included. So that is a closed interval. This is a half open, half closed interval. In this case, the right endpoint is not included in the interval, but the left point is. In this case, the left endpoint is not included, but the right endpoint is. We will never, under any circumstances, ever have a bracket next to positive or negative infinity, because we are never there. All we can hope to do is get near. How near? Arbitrarily near. So we will never include positive or negative infinity in our intervals. They must always be enclosed by a parenthesis. So there's set notation that I want to make sure that you know. Let's talk about the analytics of absolute value. We've talked about graphs of absolute values and translations and reflections. Let's talk about how we actually work analytically absolute value problems. The absolute value of some number equals 7. All outputs of absolute values are positive. The result of an absolute value operation is always a positive result. So when we ask for the solutions, what x values make this a true statement? Well, there were 2 of them. That's a true statement, but that is also a true statement. There were 2 possibilities of how we would get a positive 7 out of that absolute value operation. That's why this particular absolute value problem has 2 solutions. Both of those make this a true statement, and that's what solutions for a mathematical statement do. This absolute value has only one solution, because 0 is neither positive nor negative. This equation has no solutions. There is no x value that I can put into the absolute value function and get a negative as a result. Not going to happen. So there are no solutions to that equation. Now let's bring variables into play. When we have an absolute value variable expression, and we're told that that expression equals positive 11. Well, there were 2 cases where we were going to get positive 11. One is if we started with negative 11, and the other was if we started with positive 11. So this can either equal positive 11 and still give me that result, or equal negative 11 and still give me that result. That's why there are 2 possibilities when we analytically solve an absolute value function. There are 2 possibilities. It's why we take this result and set everything inside the absolute value marks equal to the positive and to the negative, because either one of those will give us the result that they say we got. I'm not going to go through and do the mathematics here. It's right in front of you. But I just wanted to highlight why we set those problems up that way.